Strain is a concept that is more specific than deformation. It's part of the deformation. Strain is something that says, well, the strain is that part of the deformation that informs about the changes of distances about particles and angles among segments or edges in the body, which in the future we'll see are responsible for the generation of stresses. Okay? So you see, it's not the same, it's just a more restricted concept. Okay? And we have to distinguish between the words a strain, change of distances and angles, and deformation, more general, change of relative position. Okay? So in other words, we don't have enough information given that the strains. We need something that informs about the changes of angles and distances between particles. That is the strain. Look, let's see how do we approach the concept of a strain, please. Let's consider again the material configuration, the spatial configuration, two particles, P and Q, which have a relative position differential of x at the reference configuration. These two particles at the present time occupy the position P prime, Q prime, and the relative position is differential of x. We know that the fundamental equation of deformation says that these relative position vectors are related through this vector, which is called, remember, gradient of deformation tensor, material gradient of deformation tensor. Okay? And this is the inverse gradient of deformation tensor. Okay, that's all. By the way, let's now look at the distance. So far, we referred to relative position, vectors. Now look, let's think about distances. What is the distance of these two particles? Let's call it a scalar, a distance in a scalar, which is always positive, which is, what is the distance? The norm of this vector, the modulus of this vector, right? Let's call that capital DS. The distance between these two particles at the reference configuration, we term that capital DS, and the same distance, not the same, the distance of the same particles at the reference at the present configuration, small ds. Okay? By the way, how do we obtain capital DS or small ds? Well, by taking the norm, the modulus of this vector. The modulus of a vector, by the way, is just computing the square root of the dot product of the vector times itself. So if you multiply scalar product of one vector times itself, you take the square of the modulus. If you take the square root, then you obtain the modulus of the vector. So this is a scalar, which can be represented that way, which now this refers to the distances of this particle at the reference configuration, and this stands for the distance of these particles at the present configuration. The point is that, where is the information about that? Where is the information about that? Well, in part is in here, no? But here there are too much information. There are too much information. We want to just to see what part of F contains the information about the change of this distance. How that tell us how much these two particles that were initially separated at a distance differential of S at the end, at the current time, are separated at a distance differential of S small s. So the point is the following. Okay, let's just compute how much is this distance differential of S squared. Distance squared would be obtained by multiplying differential of small x times differential of small x, which is, this product is in matrix form obtained by transposing the first and multiplying matricially by the second. But now, using the fundamental equation, the transpose of differential of x would be the first transposed, that is transpose of that, and that transposed is that. To obtain that, there is a rule that says that the transposed of the product is the first times the transposed of the second. So I do that, and I obtain this equation, okay? This equation that says that this differential of s squared is equal to differential of x times f transposed times f times differential of x. So what does this say? This says that, in fact, that information about this length is contained on the gradient of deformation tensor. It's contained on that, okay? But it's maybe too much contained. Let's see if we can just filter a little bit this information. By the way, I could also compute what is this capital differential of S by doing this operation. I multiply differential of capital X times itself, I obtain differential of S squared, I replace the inverse equation of motion here, and operate, and obtain this equation, which says that this information is contained on F minus 1. By the way, F minus T stands from now on to the inverse transposed. Okay, so I take that in order not to put two superindex, something to the minus 1, that stands for something, to the minus 1 transposed will be denoted by this something to the minus transposed. Okay, well. So this equation says that this magnitude, a scalar, is a magnitude, is the information on that depends, of course, on differential of x, but small x, but also essentially on the inverse of the gradient of the deformation tensor, or the inverse gradient of the deformation tensor. Okay, now in terms of that, operate a little bit, then just do the difference. So now we do the difference of this minus this square. So now we are concerned about what is the difference of the square of lengths. Now we want to see the variation of lengths. So now I want to compute this distance square minus this distance square. And doing these operations, I find, after replacing some of the equations, I find that this difference can be expressed in that way. Look, differential of small x times something times differential of right x. That's a product that it can be proven that this is a scalar. So this operation provides the squares, the difference of the squares of the distance of the two particles before minus after. Okay? But what is interesting is what I've obtained here in these operations. This is 1 minus f minus t, f minus 1. Sorry, maybe I just, look, I do the same, just skipped one difference. I see that this difference can be expressed in differential of capital X, and here something. Something that is f transpose times f minus 1. Okay? Well, this, I define that as twice an entity, which is called capital E, which is the first measure of a strain, the most important measure of strain. This is the Green-Lagrange or material strain tensor. So, after this is algebra. I can say that we have defined a tensor, second order tensor, which is defined as 1/2 of f transpose times f minus 1. By the way, by expressing that in components, aij will be 1/2. What is the component ik transposed is ki times component kj minus delta ij. That's just the definition of every component ij in terms of the components of f. And this tensor, Lagrangian or material strain tensor, has a property. Look, if I multiply that tensor times the left by the relative position of the two vectors before the deformation, and times the right, at the right, times the relative position of the two vectors, this returns a scalar which informs about the change of distances. Informs about the change of distances because it says, well, informs about what is the difference of the square of the distance of the two particles after the deformation minus the square of the distance before the deformation. So that guy here informs about distances. Indirectly, if you wish, but informs about distances. And that is the most important issue of this guy. This is something that this entity is extracted from f. Look, so to compute that, I just have to compute f. But it's not exactly f. It's something different of f. If f transpose times f minus 1 divided by 2. Okay? And this guy has the property that multiplying it times the relative position of two vectors before the deformation, before the movement, returns the change of the square of the distances of these particles. Okay? That is the most general definition of strain. Probably you are already familiar with strain. We are familiar as engineers, and since we have been taking some courses on structural mechanics, you know what is the strain. But the strain that you know is a very specific, very reduced, very simple notion of a strain. We see that this strain, we'll see, just turns into the one that you know for a specific case. When the deformations are very small. Otherwise, they are different. We'll iterate about that. That's a very important concept. That's new for you. Strain is not what you know. Strain is something more general. The strain is that. But this, we'll see that for specific cases, turns out to be what you are used to, the strains that you are dealing with. You do a strength of materials. Okay? And the abstract concept of a strain, this tensor, is that it informs about changes of distances. We'll see that it informs also about additional issues. We'll see. But so far, it informs us by this operation. It can tell us what is the change of distances of the two particles. Okay, properties of this tensor, it's symmetrical. It's very easy to see. What is a symmetric tensor? That when I transpose it, it's the same. That's what you find in symmetric tensor. If we transpose that, we can see here that transforming, for instance, what happens here if I change I times j? So instead of Eij, I compute Eji. What happens? The result is the same. Because this becomes a j, this becomes an I, but the result is the same. So this is a symmetric tensor. That's important. Okay? So this tensor, Aij equal Gi, is expressed that E transposed is equal to A. It's a symmetric tensor. Symmetric tensor. Okay? So across the diagonal, if we do mirroring across the principal diagonal, we obtain exact values. Okay? Okay, let's do now something similar, but now looking at the difference, but trying to see how this is difference, the difference of the particles before square minus, after minus before square. Let's try to express the difference now in terms of the position of the particles after the deformation. Here, we have the position of the particles before the deformation, right? So now, we have to do some algebra too. The differential of E small square is differential of x times differential of x. Here, this is the result that we obtained before, and we obtain this expression here. That is very similar to what we obtained before, but now, instead of having the difference of the squares in terms of the position of the vectors before, now we have the position of the vector at the present time. So after the deformation. Okay? And this is what we call another tensor, which is small e. The small e is called the Euler-Almansi strain tensor or the spatial strain tensor. I'm sorry, you have to keep some of these concepts in mind. I mean, you have to give names to the entities we are discovering, but every name tries to be consistent with the physics of the problem. No? This tensor defines the difference of distances in terms of the spatial current relative position of the vectors. The other one defines the difference of lengths in terms of the material current reference configuration of the vectors. That's why this is called material strain tensor, and the other is called the spatial strain tensor. And this strain tensor turns out to be this way. Look at this different. I mean, that definition is not the same than this. It's another tensor. They are not again, this is not the material description of the other, or the other is not the spatial description of this. They are different tensions. Of course, they could be eventually defined in every description, material or spatial, but they are not the same. Why? Well, because they inform about the same distance, but through different operations. If they were the same, here everything would be the same. But due to this distance can be evaluated either in terms of the material strain tensor by multiplying by the capital differential x, or with the spatial strain tensor by multiplying by the small differential of x. So these two strain tensors are not the same. Both are symmetrics. Both are symmetrics. That can be proven that the spatial grain of tensor is also symmetric. The Euler-Almansi or spatial strain tensor is also symmetric, but they are not the same tensor. no, we cannot say that the spatial description of the material strain tensor is not the spatial strain tensor. Okay? Taking time. So, now some additional operations. We got something, going back a little bit, what we saw before, we got the talk, when we talk about deformation, we just introduced the gradient of displacements. And we saw that there is a very simple relation of the material gradient, which is the gradient of the deformation tensor minus 1, or the spatial gradient of displacements, which is 1 minus the inverse gradient of deformation, right? So now let's take advantage of these expressions and see how these entities that we have defined, which are very important, this is one of the key issues of this course, the measure of strains. These ones can be defined in terms of f or in terms of f minus 1, but now we're replacing the equations f minus 1 equal 1 minus j or f equal j plus 1, we can replace them into the expressions and we obtain alternative descriptions of the strain measures, material strain tensor capital E, a spatial strain tensor small e, in terms of the displacements, okay? Which is more similar to, this is the first approach to your concept of strains. How do you obtain strains, remember, in structural analysis? Derivative of displacement, you remember? So here, strains are obtained are derivative of displacements through this formula. Look, it's not so trivial. So here we have Aij is 1/2 of derivative of ui with respect to xj, uj with respect to xy. And then here there is the product. There is here is a mute index here. So that means that there is a product here, a summation. Okay? We'll talk about that. That is responsible that these strains are different of the concepts that of the strains that you are familiar with. I anticipate that the strains that you are familiar with is that part. And that part is the additional one that sometimes becomes negligible. And then it returns what you are used to. But the most general expression of strains in terms of the derivative of displacements is that in terms of the spatial material derivatives of displacement, or that in terms of the spatial derivative of displacements. Okay? Let's do this example. For instance, let's consider this motion. This is the equations of motions in matrix form, and let's obtain the strain tensors. Okay, that's the motion. That's the gradient of the deformation tensor. We have obtained that before. That's the inverse of the gradient of the deformation tensor we have obtained before. So now imagine that I want to obtain the material strain tensor. So here formula, we look at a formula, I see E is 1/2. F transposed, I take F and I transpose it. So look that I change columns by rows. I do the mirroring with respect to the diagonal, principal diagonal. So this term comes here, that only change. F times F, I put F again. I do the product. Matrix 3 times 3 times 3 times 3, that's a matrix. I subtract the unity tensor, which is which has 1, 1, 1 at the diagonal, that's the unity tensor. And I do the operation, and that's the result. That is the gradient of the deformation tensor. Sorry, that's the material strain tensor or Lagrange tensor. Look, it's symmetric. It should be. If it's not symmetric, you have made a mistake. It is symmetric. Look, that term is equal to that term, that is equal to that is equal to that. Symmetric, okay? Okay, this is for capital E. Okay, what about the small e? So the spatial measure of strains, the spatial strain tensor. We look to the formula, and we see that E is equal to 1 minus F2 minus transpose to F minus 1. Okay, I place 1 here. This F2 minus 1, I have to take the inverse of the equations of motions, we have obtained before. I place this transposed, which is this. I multiply by f to the minus 1, which is that. I do that product, I do this operation, and obtain that. So this is, this is the material spatial strain tensor. That is the material strain tensor. Is it the same? Well, we can wonder. Well, in fact, I cannot check yet because this is given in material description. This is given in the spatial description. Okay? But I can realize without no further operation that they are not the same. Why? Because look, if I do the spatial description of heads of here, so if I replace here the inverse equation of motions, I would obtain some expression. But this one, for instance, will not change. Okay? Because there is no x, y, and z involved here. And look, if I compare this term with respect to that, it's different. So they cannot be never the same. I mean, just it's a simple way to see that they are not. Of course, you want to be checked. You can just take the effort and replace here the inverse equation of motion, and we'll obtain the spatial description of the material strains, and we'll obtain something in terms of small x, small y, small z. Or you can go here and compare it with here. Or you can replace here the equations of motions, and we obtain the material description of the spatial strain tensor, and we obtain something in terms of capital X, Y, and Z that you can compare with that. And you will see they are different.